Hello and welcome back to geometry. Before starting today's topic, we're in the beginning of chapter 2, so make sure you complete the before you read activity here, deciding if you agree or disagree with each of the following statements. And on the second page, don't forget to follow along as you complete each section. Go back and fill in some key points or your favorite facts that you find from each section here. That'll make a great study tool for you at the end of the chapter. Now for today, we will cover section 2.1, Inductive Reasoning and Conjecture. So the first thing we're going to do, look at what we'll learn. Scan lesson 2.1, list 2 headings that you would use to make an outline of this lesson. So let's take a look up here. We've got heading number 1, make conjectures. And I can immediately see the vocabulary term inductive reasoning there, so I'm assuming there's a connection here without finishing reading the sentence. I think we can safely write first heading, making conjectures with inductive reasoning. Making conjectures with inductive reasoning. I guess that's not really a full sentence there. All right, and what else? There's an example, another example, real-world examples, and finally a second heading, find counterexamples. Well, that sounds like a direction all by itself. We don't need to know what counterexamples are, but we are going to find them. Counterexamples. Okay, so let's dive into the meat of the lesson and find out what these things really mean. As we read, we will return to the active vocabulary here and fill in each blank with the correct term or phrase. So we have the vocabulary given, we've got the start of a definition provided there. So back to the beginning of the lesson to begin reading. Number 1, make conjectures. Inductive reasoning is reasoning that uses a number of specific examples to arrive at a conclusion. When you assume that an observed pattern will continue, you are applying inductive reasoning. An observed pattern. It's a good way to think about it. A concluding statement reached using inductive reasoning is called a conjecture. Okay, we have our first 2 vocabulary terms there. Inductive reasoning is reasoning we'll have to write small, that uses a number of specific examples to arrive at a conclusion. And then we had a name for that conclusion. The conjecture is the conclusion that is reached within inductive reasoning. So it's not something you're absolutely certain about, but it's something you predict. It's like a prediction of how the pattern will continue. We will do the examples in full detail in part 2, but I think it's useful to get a visual of what type of thing this means following patterns here. Take a look at following the movie show times. We're counting along the times there. We're drawing bigger and bigger squares, counting series. Here's more and more triangles going. So different types of patterns. Following that pattern is creating conjectures. To make some algebraic and geometric conjectures, you will need to provide examples. Okay, so algebraic and geometric, instead of the full list of things, the pattern is not presented to us. It's an idea from which we could create a pattern, the sum of two odd numbers, so they start making some examples of odd numbers to see what the pattern is. And we could also form real-world conjectures, often made based on data gathered about a specific topic of interest. I think that makes sense. Pick your favorite topic from science class, you take a bunch of measurements, you find the pattern, create a conjecture from that. All right, how about section 2, find counterexamples. To show that a conjecture is true for all cases, you must prove it. It takes only one false example, however, to show that a conjecture is not true. This false example is called a counterexample, and it can be a number, a drawing, or a statement. So there's our third vocabulary term, counterexample. An example that, we only got 2 blanks there, shows conjecture is false, doesn't really quite fit. How about an example that disproves a conjecture? So if you say, predict that all cars are red because you saw a lot of red cars, all it takes is one blue car to drive by and suddenly your conjecture that all of them are red has been disproven. Well, all but that one at least. Conjecture is a word that is used in everyday English. Find the definition of conjecture using a dictionary, right? How the definition of conjecture can help you remember the mathematical definition of conjecture. I didn't prepare my dictionary ahead of time. Let's see if I can pull it up on the apps here. Let's find conjecture. I like how it automatically suggested counterexample as another one. Noun, the formation or expression of an opinion or theory without sufficient evidence for proof. We had previous examples, but we didn't have proof there. An opinion or theory so formed or expressed. A guess, speculation. Okay, so opinion, guess, speculation are all in there. I hope that gives you an idea of how uncertain it can be. So, opinion, guess, speculation. I earlier said prediction. All of which means it is not 100% certain. It's not a ridiculous, unfounded guess, but it still could be easily proven wrong. All right, after the example of a counterexample, do we have any more text to read? Nope, there's the check your understanding. So let's return to the beginning and prepare for the main idea. Making conjectures. Sequence the steps of making a conjecture with algebraic terms or geometric terms. Let's see, algebraic or geometric. I think that was in example number 2. Algebraic or geometric. Aha! I see 3 steps. Was there 4 steps in here? I see 4 boxes, but only 3 steps. Perhaps the last step is, well, let's see, list examples, look for a pattern, make a conjecture. I'm not sure where they're getting that 4th step from. Supporting examples and proofs. Examples that support a conjecture are not enough to show the conjecture is true. To show that an algebraic or geometric conjecture is true, you must offer a logical argument called a proof. You will learn more about proofs in lesson 2.5. Okay. Well, how about, well, we'll start with the 3 steps given. We will list examples. We will look for a pattern. Don't know why that's such a large box. Then over here, make a conjecture. And then I'm going to add, as a final bonus step, test the conjecture. So basically trying to find any counterexamples if you can. All right. Now for finding counterexamples, write a statement in which you can make a true conjecture. Then write another statement in which you can make a false conjecture. Provide a counterexample of the false conjecture. A statement in which you can make a true conjecture. I think the statement itself is a true conjecture. Let's see if I can think of something geometric here. They've got other segments joining opposite vertices of a rectangle. Sum of 2 squares. That's all numeric based. I'm going to think of something a true conjecture. All triangles have an angle sum. I was about to think of all triangles have 3 sides. Well, that's by definition. That's not very impressive. Have an angle sum of 180 degrees. So that's something we could test, we could check, we could try each triangle. If you find one that doesn't have 180 degrees of the sum of its angles, then you have disproven my conjecture. And then a false conjecture that we could provide a counter example to. Let's see here. Well, there was something about the squares and the rectangles. Okay. Here's one. All parallelograms are rectangles. We do a lot with rectangles. Maybe that's the most common seen parallelogram. For our counterexample, I'm going to draw a picture. There's that. There's that. And there's that. And so these, I'll go in red. These 2 sides are parallel to each other. These 2 sides are parallel to each other. It's definitely a parallelogram, but those are not 90-degree angles. It is not a rectangle. So there you go. Not all parallelograms are rectangles. Now, to help us remember, could we write a short sentence that can help you remember why it only takes one counterexample to prove that a conjecture is false? Well, I want to go outside the realm of mathematics here. Let's go a little bit abstract. Why does it only take one false thing to undo all of your work? It's the same as any instance where it only takes one negative aspect, one bad instance in order for something to stop working. So think of something very complicated, right? Like a car engine. It only takes one bad part to stop a car from working. One bad part to stop a car from working. Or more simple, how about this? It only takes one hole to make a bucket useless, right? You could put a lot of holes in it, but you only need one to ruin the whole thing. So that's the idea of a counterexample. It only takes one to have a bad day. All right, and that concludes the guided notes for section 2. Come back for part 2 to complete the example problems from the section. So long, farewell. Enjoy the rest of your day.